Namaste, welcome to Pythagoras Academy. This is Vikram Dachepally. In this video, I am going to discuss the concept of string constraints. Consider a string of some length. A and B are two ends of the string. Two ends of the string can have velocities in different directions. And I am resolving the velocity of A, and I am taking the component of the velocity of A along the string. I will name it as VA. I shall resolve the velocity of B and take the component of B along the string. I'll name it as VB. A can have velocity in this direction, in some random direction. So it is making some angle theta with the length of the string. So if the velocity is V, that V cos theta is VA. Similarly, B can have different velocity in different direction. The component of velocity of point B along the length of the string, I am naming it as VB. So basically VA and VB are the velocity components of points A and B, not the total velocities. VA and VB are the velocity components of points A and B along the length of the string. Then the condition, if VB is greater than VA, obviously the string breaks. If the end B is moving along the length of the string with a velocity greater than that of end A, definitely the string would break. And if VB is less than VA, VA is faster than VB, then in that case the string is slack, the string is no more tensed, the string is slack. In both the cases, if the string breaks or string becomes slack, the tension in the string becomes zero. If at all the string is taut, it should satisfy the condition that VA must be equal to VB. Implies string is taut. This simple logic we are going to apply to deal with string constraints. If two ends are connected to two different blocks or two different points in a mechanical system, always along the length of the string, the velocity components must be equal if at all the string is taut and tensed, if there is some tension in the string. Otherwise, the string would either break or become slack. So the mechanical system is not working. If at all the system is working, the string is taut, and if the string is taut, it has to satisfy this condition. So this is the logic that we are going to apply in order to deal with string constraints. The same thing can also be applied for a rod. If it is a rod, there is no case of rod breaking or rod becoming slack. Definitely the velocity components of the ends of the rod must be equal along the length of the rod. Let us see one example. So consider a rod which is sliding between two perpendicular frictionless walls. The velocity of end A is along the vertical, it is VA, and velocity of end B is VB in the horizontal direction. At an instant when the rod is making angle theta, I have to find the relation between VA and VB in terms of theta. If this is the question, if I apply this logic, it is very easy. With just one step, you'll get the answer. Let us see the regular constraints method first. Then we'll go to the shortcut. The regular method is this. So you can consider this distance to be some y, and this distance is x. X square plus y square is equal to L square, where L is the length of the rod, which is always constant. X and y will change such that x square plus y square is always equal to L square by Pythagoras theorem. Now differentiate this. So 2x into dx by dt plus 2y into dy by dt, that is equal to 0. So x into dx by dt, the rate at which x changes. So given the directions of VA and VB, VB is in the direction of increasing distance x. So dx by dt is positive. So I'll write dx by dt to be plus VB, whereas dy by dt, the direction of VA is in the direction of decreasing y. So y is decreasing, so dy by dt is negative. So I'll write dy by dt as minus VA, which is equal to 0. So VB is equal to y by x into VA. So VB is equal to VA. In the figure, y by x is tan theta. This is the constraint equation. But now if I apply the concept of the velocities being equal along the length of the string or along the length of the rod, so this case is going to be very, very simple. So instead of getting these many steps, instead of doing differentiation, instead of getting constraint equation, just one step, the problem is solved. So shall we do that? So this angle is theta. So this angle is also theta. The component of VB along the length of the rod is VB cos theta. Now similarly, so this would be 90 minus theta. The component of VA along the length of the rod is VA cos 90 minus theta. I just have to equate these two velocity components. Very simple. So VA cos 90 minus theta is equal to VB cos theta. So VA sin theta is equal to VB cos theta. So VB is equal to VA tan theta. Just one step. It's done. So simple will be dealing with strings or rods by applying this concept of velocities of the ends along the length of the rod or the string being equal. Let us take another example. So consider this pulley block system. So there are three blocks M, M and M dash. Now at a given instant when this string is making angle theta with the vertical, you are supposed to find the relation between V and U. The question is, what is the relation between V and U? Or given U is given, you are supposed to find V. The two blocks of mass M each are moving down with a velocity U. At that instant when the string connected to M dash is making angle theta, in terms of theta at that particular instant, how do you find V in terms of U and theta? You can again do by normal constraint method, like you can take the distance, this vertical distance to be y, this distance along the string to be x, so dx by dt will be u and dy by dt will be v, and you can apply Pythagoras theorem, x square, so you can take this as y, this as x, and this is some distance d, so x square is equal to y square plus d square, x is the hypotenuse, x square is equal to y square plus d square, differentiate, you can get the relation between v and u. But instead of doing all that, with just one step, I can get the final answer. How do I do that? Simple, let this velocity be v. The component of this velocity along the length of the string is v cos theta. And the other end is this. The component of the velocity of this end along the length of the string is complete u, because u is already directed down. Now v cos theta must be equal to u, so v is equal to u by cos theta. Very simple. This is how you get the value of v. Many students, when they encounter this problem, they get into misconception that they assume that velocity of the, so they take the velocity of the string to be u in this direction, and they resolve this u and they write u cos theta is equal to v, which is absolutely wrong. U cos theta is not equal to v in this case. V cos theta is equal to u, because the component of velocity of the end of the string along the length of the string is v cos theta, that is equal to velocity of the other end, that is u. So v cos theta is u, v is equal to u by cos theta. So this is how you deal with string constraint equations. Thank you. If you have any questions or queries or suggestions, you can always use the comment section to interact with me. I'll be more than happy to respond and receive your feedback. This is Vikram Dachepally signing off Namaste.